So, welcome to Limits. I guess officially your first day of calculus. I think we could think of it that way. The way I like to think about limits is like this: you have your algebra, big old pot of boiling algebra. Probably got some geometry in there too. You know, all the math that you've learned. Probably some trigonometry sprinkled in. But that's what it is. It's just this pot of your basic math. And we got this nice big bottle of limits here, right? And what we're going to do is we're going to pour some limits in. I know what you're thinking. You're thinking, no, that's crazy. Don't do it. Don't do it. What's going to happen? Okay, I was okay. Not that there's a little more. Oh, I know. I know it's dangerous because at any time, if I put too much limits in it, and that's what makes algebra turn into calculus is limits. You cannot have calculus without limits. So this is big stuff that we're going to be learning, but don't freak out because it starts with just ideas, and we're going to build those ideas up toward what we're going to really call calculus, and that's where you'll kind of pick up next year. So no heavy stuff, just important stuff. This is page 3-1 of the notes packets that you guys got the, on the last couple days that we were able to meet, and let's dig in. The concept of the limit, as we just talked about, is the big idea that really distinguishes calculus from algebra. Um, and remember way back in the beginning of the semester, we had a real hard time defining continuity. We're going to be able to use limits to help us with that too. The definition of a limit here is letting C and L be real numbers. So we're not going to deal with any imaginary complex numbers in this. C and L are real numbers. The function f has a limit L as x approaches C, only if the limit of f of x as x approaches C is L. So that's how you read that. The limit of f of x as x approaches C is equal to L. And that's kind of how you work your way through it. So let me break that down for you. Okay, the limit of f of x as x approaches C is equal to L. Okay. If this was algebra, we wouldn't have any limit, right? There'd be no limit. And we would just do what we call substitute. We would evaluate the function f at C. Now, what we're going to find is that in nice cases, that's exactly the same thing as what we're going to do with limits. What do we mean by nice cases? Well, that'll be part of our discussion, but that's not necessarily always the case anymore. So the limit's going to change the games. Now, I do have here more of a calculus-y definition of limits. It kind of throws people off a little bit because we get into a couple new symbols that you haven't seen before. This is delta. You guys know what delta means all the way back from algebra 1 when we talked about change, and the only difference is, see, here's a capital delta here, right? Like the triangle, that's a capital delta. It was like change, right? And it still means change. You'll see quite a few of those pop up in this unit. But this is a lowercase delta, and then this is a lowercase letter called epsilon, delta and epsilon. And so this definition, I remember the first time I took calculus and I saw this definition, it took me a couple days to wrap my mind around it. So don't worry about it. But let f be a function defined on an interval that contains some x value a, okay? And we will say that the limit of f of x as x approaches a is equal to L if for every epsilon, positive epsilon, there is some, so for every positive epsilon, there is some delta such that we're guaranteed that the difference between our function and the limit being less than epsilon, our the difference between our x values, x and a, is guaranteed to be positive still, but less than delta, less than delta. So the picture kind of illustrates what's happening. Your epsilon is a difference in y values. It's either epsilon up or epsilon down, right? You can either add or subtract an epsilon. Your delta is a change in x values. You can either add or subtract delta from your a. So what we're basically saying is that no matter what epsilon we pick, you get to pick any epsilon you want, which means I could pick a tiny, tiny epsilon, and I'm guaranteed that as these lines right here get really, really tight around that y value, really, really tight, there still will exist a delta which will force our epsilon to fit between those values. So the delta must exist that does this. They put it in a nice way here. It's probably too small of a print for you guys to read, but it says that what the definition is telling us is that any number epsilon greater than 0 that we pick can go to our graph, and we can sketch two horizontal lines such that L plus epsilon and L minus epsilon, so those are the two horizontal lines we see right here. Okay. Somewhere there's going to be a delta such that we can determine that our function's y value will be between those two lines. So it's a more complex, like I said, more calculus-y definition. So you don't have to worry about that right now. I put that to you because I never remember seeing that specific definition until later on in calculus, and it freaked me out. Right now, what's really important is you understand what a limit is, and that's what we're going to talk about in this lecture. What does this more simplified definition mean? But I did want you to just to see this one so you can start to equate that these two things are really saying the same thing. Here is a fundamental idea. There's a big one in trigonometry I tried to get people to understand, which is no matter which trig function you're using, sine, cosine, or tangent, no matter which one we're using, they're always just going to give us ratios. The sine of an angle is a ratio. The cosine of an angle is a ratio. A trig function is a ratio. So let's do the same thing. Let's simplify what a limit is. What is a limit? If we look at our picture over here, right, we can see that as x is approaching c, so as x is getting really, really close to c, our function should be approaching an L. What is an L? Well, it's on the y-axis, so I think that a limit has to be a y value. But what is any y value? It's just height. And that's really what a limit is doing. A limit is just a height, right? A height that our function wants to try to get to. Our function intends to achieve that height. And that's the difference between limits and just regular algebra, is when we evaluate a function, as we get close to an x value, our function will achieve a height, if at all possible. That's the answer. That's the y value that comes out of the function. Well, with limits, it's not the height itself. It's that we're intending to get to a height, which implies that it doesn't really matter if we make it to that height as long as we're getting closer and closer to it. And that is a crazy concept. That's a very highly conceptual concept, so we're going to spend a lot of time talking about that idea. Here's a little GIF that shows that the x's are getting really, really close to 3. Look at those x values. What are y values getting really, really close to? Well, 4.94, 4.96, 4.98. It looks like it's getting really, really close to 5. Now, this is a continuous line. This is just a line. So any limit is going to be exactly equal to the point that's actually on the line. If all of the functions we dealt with were like this, then limits would be unnecessary. Okay, limits really are more important when we can't get somewhere. Here are two examples built into your notes page. And the first one is one of those where it's very intuitive and obvious exactly what's happening. We have just our regular x squared, parabola, and we know what that looks like. We've known what that looks like from Algebra 1. Now they want us, it looks like, to take a couple different limits. They want us to take the limit as this function goes to 0, and then as it goes to 2, and then as it goes to -2. Okay, and so what y value, right? What height is this function getting as my x's get really, really close to 0? Well, it looks like we're getting really, really close to a height of 0. And guess what? That was the answer. That was the answer right here, 0. Okay. Now, what about 2? What happens as we get really, really close to 2? The x's are zooming in to 2 from the left, from the right. What's happening? Well, up here, it looks like our height that we're getting close to is 4. Okay, now that shouldn't be surprising because 2 squared is 4. And like I said, anytime that you have these predictable continuous functions, these problems aren't terribly challenging. We see that any time that you have a continuous function, your limit is the actual value of the function at that point, right? Same thing at -2. These tables kind of indicate what's happening, although I have some better tables down here off the newer calculators that show that instead of just going, toward 2 by ones, I'm actually going towards 2 by 0.01s. And so you get a better sense of how very close these values are indeed getting to 4. Now, once again, because this is a continuous function, the limit is equal to the y value there, and that's going to be a big idea that we talk about in the future. Okay, but for now, we just want to know what the limit is equal to. This problem, this example 2, is a much more interesting problem because when we take a look at sine of x divided by x, which is a trig function you're familiar with, but then put into a rational function that makes it totally different than anything you've really seen, it becomes a different beast. Okay, we're taking the limit of sine of x over x as the x's approach 0. So here we go. The x's are getting closer and closer to 0. Okay, what are the y values doing? Well, it looks like they're getting really close to 1, right? But when I look at this table of values here, at 0, I don't hit 1. There's an error. Now, why would that be the case? Let's take a closer look at this, right? Why would there be a problem when I put a 0 into this function? I'm sure you guys, if you were in class right now, would be telling me because Mr. Yancek, you cannot divide by 0. And you'd be right, of course. When you divide by 0, you get undefined values, don't you? In fact, this would be an indeterminate value because the sign of 0 is also 0, and 0 over 0 is indeterminate, which, if you remember, doesn't create asymptotes. It creates poles. So that's why at 0, we run into a problem. Okay? This is where limits are different, though. Okay, if you said what is f of 0, if you said what is f of 0, I would have to say the answer to that is undefined. Right? I would have to say, is equal to undefined or does not exist. Okay, because you can't have undefined values in the real number system. But we're not asking in this problem what f of 0 is. We're asking what the limit as f approaches 0 is. And although there's no doubt that I have a hole right here, okay, without question, at x equals 0, I have a hole at the point 0, 1. The limit does not care about what's there. The limit cares about what we're approaching. In both the graph, right, here we go, up towards that height, and the calculator, 0.98507, 0.99335, 0.998, right, are getting closer and closer to a value of 1. And the limit is 1. It's a crazy type of problem you've never done before. But that's what limits want. Limits want to know what you're zooming in toward, what you're approaching, what you're intending to get to, not what you actually do get to. So here's three really similar looking problems. They all look like the same line until you look at them closer. This first line is actually a rational function, which means we have a problem at 1, right? We can't divide by 0, so I can't put a 1 into this. Now, is it a whole or is it a horizontal asymptote? Well, a little bit of algebra, factoring the top as difference of squares, tells us that once these dudes cancel, dudes, there we go. All I have is x plus 1. So that means it's a whole, not a vertical asymptote. And sure enough, if we zoom in, we see a hole there. Okay, there's your hole. The function is not defined at f of 1. It has no value at f of 1. It's undefined. But the limit, as I am racing towards 1, right, as the x's get closer and closer to 1 from both sides here, the y values are getting closer and closer to a height of 2. We can never get to that height because it's undefined, but the limit is still 2. Now, what we did in example B is we fixed the hole. Remember that holes are actually called removable discontinuities? Well, that's because we can repair them. Now, I guess we didn't actually repair the discontinuity, but we repaired the undefined value. They could have quite easily said that, oh yeah, let's call this a 2, and then we would have plugged that hole perfectly. But they want you to see that even when the y value is different than the height we're approaching, the limit still exists. Okay, notice that the limit is still 2 because our graph is still getting closer and closer to a height of 2. Limits don't care about what's there. They only care about what value you're approaching. Okay, big concept. Notice that g of 1 is not undefined this time because they told us up here in the piecewise function that the g of 1 is equal to 1. Okay, the limit is not equal to the function's value, and that's going to play a big role eventually. But as far as the limit existing, it has no bearing. The last one is just a line. It's not a rational function. It's just a linear equation. We're defined everywhere, including at 1. And so this time h of 1 is just equal to 2. And guess what? The limit continues to be 2, right? We're still getting close. So when we go back and we look at all of these three problems, very similar problems side by side, here's what I want you to notice. Okay, the defined value of the function is different in every one. One of them is undefined. It doesn't even have a value. The other two have heights of 1 and 2, respectively. But the limits on them are all exactly the same because all three graphs, as the x values zoom in to 1, they all are approaching a height of 2. And I guess this is a really important concept that I want you to understand, okay? It is that, if I can find it, the existence of a limit as x approaches some value c never depends on how the function may or may not be defined at c. Okay? That's not what's important. We're going to find out in a couple minutes what's important for a limit to exist. But it is not what's happening at that point. Okay? What it is what the two sides of the function as you're zooming in on that are they agreeing with the heights that they're coming towards? That's what we'll be getting to here in a second. So don't worry about what's there, worrying about what we're coming toward. Okay, important idea, very conceptual. Okay, hope you guys are hanging in there. The existence of a limit as x approaches c never depends on how the function may or may not be defined. Okay, at c. The limit may exist at c, even though f of c itself does not exist, like with the whole. Okay, now does this happen every time the limit doesn't exist at a point, or the function doesn't exist at a value? Absolutely not. We're going to see some cases where there's big problems. Okay, now these are your properties of limits, and they're pretty much properties that you've seen with so many other real numbers situations along the way, and they continue to be true. There's two really nice situations, the simple ones. If you have a constant function, horizontal line, right? The limit is always going to be equal to the only y value that we can produce, no matter what you take the limit at, which x value you take the limit at, it's always going to be the height of the horizontal line. And with the identity function, which is just y equals x, well, no matter what the x value is, the y value is going to be the same. And so you're always going to get a limit that's equal to the x value you started with. So if you take the limit as you approach 4, you're going to get 4 for the limit, and so on. Pretty simple, but good to know. What's more important is these properties here, which is if I take the limit of two functions that I add together, and it looks like one of the functions had a limit of L, and one of the functions had a limit of M, right? Well, the limit of the sum of those two functions is just the sum of the limits. And this idea is true for differences. It's true for products. I just multiply the limits, and I get the limit of the product of the functions. If I multiply one function by just a constant, then all I have to do is multiply that limit by the same constant, and I'll get the new limit. All right. Now, it's also true for quotients, but of course, we always have to be careful with quotients. What? With the denominator, right? The denominator is not equal to 0. So what are these properties come into play? Let me show you a couple examples. By the way, this is just an example here. If we take the limit of the f of x plus g of x, right? S, and I'm just looking at this little picture I made here. The f of x plus g of x, as x approaches 5, and one of the limits is L, and one of the limits is M. I'm just going to add those two numbers together, and that'll give me what the sum of the two functions would give me at 5, basically, is what that's telling me. Okay. So here's where you would use these properties. Here's the limit of x cubed plus 4x squared minus 3 as x approaches c. All I'm going to do is I'm going to break the sum and this difference up using those limit rules. I break the sum and difference of the limits up, and then I can just evaluate them. And when I evaluate means you plug in what you're approaching. Now notice that I'm not approaching a known value here. I'm just approaching some arbitrary value c, but c cubed plus 4c squared minus 3. People will always ask, Mr. Yitzhak, do I really have to show that step? Can't I just plug the c in right away because I know that I'm going towards c? And my response to that is going to be, if it just wants you to evaluate the limit, then I think that that's absolutely fine. Yes, you can do that. If the directions say, please use the properties of limits to demonstrate this, then you actually do need to go through this step right here. So it's really depending on what the directions say. These say use the properties of limits. Look at example B. The first thing I'm going to do is I'm going to take the limit of the numerator divided by the limit of the denominator. So I'm using that quotient rule. And then I'm going to break the top and bottom up using sums and differences. And then I can just plug the c's in. Sure, I could have just plugged c's in right from the beginning and got the same thing. Once again, if it just says to evaluate it, just plug them in. You can actually go straight from this step to this step immediately. But otherwise, you do want to, use the properties of limits if they ask you to. All right, moving along here. Interesting. Don't know what that dude's doing hanging out there. These are some problems, and they should be worked out in your notes already, where we actually can just use substitution to find limits. And we're going to find that any polynomial, we can use substitution 100% of the time. In most rational functions, radical functions, we can use substitution most of the time. There's really certain times when we can't. So this is just a polynomial. And so what that means is I can just substitute the 2 in. Notice it didn't say to use the properties of limits, so I can immediately do my substitutions. I plug the 2 in and I get my answer. Now, I will say that sometimes uh, people leave this step out and they just do it in their head, and you can't do that. You have to show substitutions. It's a critical step in this process. If you skip it, you're not doing the math right, and you're going to lose points for that. So please be careful about that. Example B. Once again, I'm going to go ahead and plug that 2 in. Now I could get in trouble if I plug in a -2, couldn't I? But I'm not approaching -2. I'm approaching +2. So I'm okay. So I'm going to plug that 2 in. I'm going to follow order of operations and simplify it, and I get a 3. Okay. When you can use substitution, which is what primarily you're going to be doing on tonight's assignment, life is good. And so tonight will be a pretty good way to ease into this. This last one is not a polynomial function. It's a root function. And I just substitute the 9 in because this function is defined at 9, and so the limit's just going to be equal to the function's value there. Anytime the limit is equal to the function's value at a point, substitution is going to work. Now notice I could get in trouble if I plugged in a 2. What's the limit as I approach 2? Well, that would give me square root -3, which is not a real number, and I would be stuck. So those are some of the things we'll start really getting into tomorrow. Non-existent limits are an example like we just talked about, right? The limit of that root function at 2 would not exist because it's not a real number. Same thing here. This time I take the rational function 1 over x minus 2, which I happen to know is not defined at 2 because 2 creates a 0 in the denominator, right? So we know that's going to be a problem. In fact, this time it doesn't cancel with the top, and so I get a vertical asymptote, right? I think I got one in here somewhere. There it is. Look at that. So what's happening to the y values as I approach 2? Well, it looks like as I come in from the left side, that's where the negatives live, right? As I come in from the left side, my y values are actually racing down the vertical asymptote towards negative infinity. On the other hand, as I come in from the right side, the positive side, I'm racing up the asymptote towards positive infinity. So first of all, these don't match. One of them's positive, one of them's negative. But more significantly, infinity is not a real number. And if you go back to the first page of your notes, the definition tells us the limit L must be a real number. And here we do not get a real number. Okay, we get arbitrarily large values. And so the limit does not exist. DNE is the short way of saying that. DNE does not exist. That's how you would call that. That's how you would say that this value has no limit. It does not exist. Okay. And if you've seen, I think this might have been from Mean Girls. I can't remember, but some of you may remember that exact scene. Yes, the limit does not exist. All right. This is really important right here. One-sided limits. One-sided limits. And I've kind of been talking about this a little bit already with you, but one-sided limits are where we're only approaching an x value from one side or the other, from the left or from the right. Okay. Now, the right limit is going to be denoted by this little plus sign right here. All right. This guy right here tells us we're coming from the right. That's where the positives live, right, on the x-axis. The difference is that with the left limit, you're going to see a little minus sign. That tells us we're coming from the left, where the negatives live. So the left limit is coming in this direction. The right limit is moving in this direction. So we're just talking about moving towards an x value from one side, not both. You really have to pay attention sometimes because it's hard to see those if the print is small. So don't just assume it's a full two-sided limit if it's not. Okay. here is how we would do these problems. The first one asks what the limit is as we approach 2 from it looks like the right. Okay, so you can see right here, if I blow this up, we're coming in from the right. 2 plus means from the right, so we're moving towards 2. Oops. We're moving towards 2 from the right. That's the right limit, okay? What height does it look like we're approaching? Well, actually, this is an open circle. It looks like the values are actually up here at a height of 2. So it looks like my y values as I move into 2 from the right are at a height of 2. On the other hand, if I move into 2 from the left, and so now we're talking about what this dude's asking us. And if you look at the 2, there's the little minus right there. That says we're moving in from the left. Okay. It says that the height is up here at 1. It's at 1 and being very constant on the way in. Okay. So the answers are here for you. The right limit as we approach 2 is 2. The left limit as we approach 2 is 1. And that creates a problem overall. I mean, one-sided limits are great, but what if I said, what's the limit as we approach 2? What's the limit overall as we approach 2? Well, do you see the problem is that we're not approaching each other. And so you would have to say that the answer as a two-sided limit here would not exist. All right? Remember with the hole, even though there was a hole, we were approaching, and I'll go back and let you look at that one again. All right? It was this example right here. Even though there was a hole, we were still approaching the same height toward that hole. The limit existed. In that case, it was a height of 2. Well, this is a different situation here. Okay, I've got 2 different heights. That doesn't work. So overall, we would say there is no limit at this value. Okay, but these that's what one-sided limits are, either right or left. And if I could just borrow your attention for 1 second here. All right, stare at the screen for me just for a second, and you may start to feel very comfortable, very relaxed. And you may be thinking about how enjoyable it is to learn math and do your math homework, and how you feel how important it is to do your math homework every single problem for the next 4 weeks, because limits are so important. And every time that you feel like you've got something better to do, like watch a show on Netflix that you're binging, or maybe play a video game, you're gonna be like, no, math is more fun. Math is more fun. Anyway, as I was saying, one-sided limits are important because the two-sided limit definition depends upon them. Okay, f of x has a limit as x approaches c if and only if the right hand and left hand limit exist, and this is the important part, are the same. You can't just have limits that exist, they have to be equal to each other. These both had limits that existed. This limit was 1, that exists. This limit is 2, that exists. But 2 is not equal to 1, is it? And so they would not have had a limit, a two-sided limit, as we approach 2. All right? This is a little GIF that shows you that when you have a hole, you're still approaching the same height. And it says, yeah, you have a limit. But now we have a jump discontinuity, okay? And first of all, there's no value at A, but second of all, the limit doesn't exist. We're not approaching each other. Same thing with an infinite discontinuity, okay? So when we're continuous, not only will the limit exist, but it'll be equal to that value. Now, when there's a hole, the limit still exists, even though the value doesn't exist. When there's a jump discontinuity, okay, you will have one-sided limits, but not a two-sided limit, even if f of a does exist at one of those heights. And when you have an infinite discontinuity, like a vertical asymptote, right, not only does f of a not exist, the limit doesn't exist either. So of the 3 major discontinuities that we discuss, removable discontinuities still have limits that exist. Jump discontinuities, the limit does not exist anymore because the heights don't agree. And with infinite discontinuities created by vertical asymptotes, the heights really don't agree. And so go ahead and watch that sequence through a couple times, or you could go to that website, I guess, where I stole this GIF from, and it really shows you how discontinuities affect whether one-sided limits exist, transferring into two-sided limits. Like here, we have two-sided limits that exist, but they're not equal, right? And so the overall limit didn't exist. So check that out. Okay, it's a good visual. Here's a two-sided limit example. Um, we have a function that's kind of a piecewise function, little pieces here and there. It looks like I have a jump discontinuity at 1. I have a removable discontinuity at 2. What are the areas of this function where it is not going to have a limit that exists? So um, first of all, you can have one-sided limits at the endpoints of intervals, and all that matters is that's all that there is. And so as I approach 0, this function doesn't exist over here, so you can only talk about the right limit. And it looks like the limit's approaching 1, right? Same thing with the other endpoint. As I approach 4, I can talk about the left limit being equal to 1, height of 1. But it doesn't have a right limit because I don't have function over here. Now, everywhere else in between, I have a two-side limit. As I approach 1/2, my limit would be, it looks like this height because they agree, right? Now the right hand limit as I approach 1 looks like it's a height of 1. The left-hand limit as I approach 1 looks like it's a height of 0. That's a problem, isn't it? So the one-sided limits exist, but they don't agree. And so we would say that overall, this function does not have a two-sided limit. And the two-sided limit is the overall limit. We would say the overall limit here, DNE, does not exist because of the two different heights. Now, what about as we approach 2? I think all through here we're continuous, we're fine. But what about as we approach 2? Okay, notice the function is defined up here at 2, but the left limit is at a height of 1, and the right limit is coming down also toward a height of 1. Oh, look, the right and left-hand limits have the same height they're approaching, and hence the overall two-sided limit does exist, and it's equal to 1. Even though the function's value is defined, right, by definition over here at 2, it still exists. Now, we don't even have to worry about 3 because we see it's continuous all the way through there. So we know the limit will exist. And it looks like the height at which we are converging to from the two sides is 2. So that's how you kind of walk through one and two-sided limits and make them connect. And that's really what it's all about. So this one is all kind of mapped out for you. I think it's explained, but you can definitely ask me if you have questions that go further than that. That's it. There's a PDF that I think finally should have hopefully uploaded. Took about 10 minutes for a PDF to upload. I don't think that's normal. Sorry about the delay with this video, but my internet has been pretty bad today. So that PDF is 3 pages. It goes through about 40 some problems. We're going to do 20 today, mostly substitution and just understanding the limits are about heights that we're trying to get to, whether they're there or not. It's very conceptual and very new, I know. So don't feel bad if you're a little bit confused, but ask lots of questions. Send me any problems you want me to go over in the solutions video for tomorrow, and I will do so. All of the answers to these are in the back of your course pack, so please use that as a resource. You're welcome to talk to each other. I'll be 3 o'clock for this week. I'll be there to answer your questions, and hopefully you guys do all right on your first limits assignment. Sorry for the long lecture, but hopefully you found some stuff in here that helped you out. Have a wonderful Tuesday.